our conference. It will be for me a very pleasure to announce the following talk. Report of Bonacci Enzo, seeding optimization in the batch crystallization of CAM. Please, please.
Thank you very much, Tatiana. So here we are, seeding optimization in batch crystallization of CAM. Another chapter in the long history of how to optimize the crystallization of CAM. It should be the final chapter. So the state of art, we all know that in 1997, the citric acid was studied a lot about kinetics, but little information was available about the crystallization by cooling in stirred tank reactors, STRs. That is the process by which the commercial product is obtained. So the Department of Chemical Engineering at the University La Sapienza of Rome decided to fill that sci-tech gap through a detailed investigation on the crystallization in discontinuous batch of the citric acid monohydrate, CAM, at San Pietro's in Vincoli's lab, DICMA. The author participated in that cutting-edge experience under the supervision of Professor Barbara Mazzarotta in the years 1997-1998. Seeking for an optimal CSD of CAM, we looked for an optimal crystal size distribution, CSD, that is large and homogeneous crystals. And we also wrote a QBasic program predicting the outcome of any tests. We conducted 20 tests. We followed a strict protocol. Those are the steps, the 8 steps we followed. Preparation of an aqueous solution of citric acid, solubilization by heating, crystallization by cooling, separation by filtration, drying exposure to air, classification of the crystalline product, analysis through the optical microscope, and pictures of some crystal specimens. We already know the best STR geometry. We talked about them in the previous AGMA conferences. That is the round tank, round bottom tank. We already know about the best STR mixing that we discussed in another conference in Odessa. That is the agitation speed 2% above the minimum value of solid suspension, and above all, a marine impeller for the axial flow. We are now looking for the best seeding conditions. What are we looking for? We want to know how big should be the seed crystals and which is the best temperature when we have to dip these crystals in the tank, in the stirred tank. And we have tested at various temperatures and various sizes of the seed. We have found light and low, light seed and low seeding temperature. This is our main result. The optimal seeding temperature is just above the spontaneous nucleation temperature. That means around 22 degrees. Here we can see the results of our tests at 22 Celsius degrees, 23 and 24. We can notice that the 22, the red line, is the best. how can we interpret these results? Well, the nucleation wave would occur at higher thermal level, originating a worse crystalline product affected by a wide granulometric distribution, poor homogeneity, and small average size. So we prefer a low temperature. The optimal seed crystal size. Seeding, as always, a positive effect, but the light seed, 1/10 of the final length of the product, is better than the heavy seed, 1/3 of the final product length, which in turn is more effective than the heavier one, when the seed is 1/2 the product's length. We can see the results of our tests. Red line is a light seed. The heavy seed is green. And we also tested the absence of seed. We wished to control if what we knew, that the seed has always a good effect, was true. And actually it is true. We can see the line that is absolutely the worst. The red line gave the best crystal site distribution. How can we interpret such results? Well, small seed crystals with a big surface volume ratio absorb a considerable share of the residual driving force. That is the difference between the solute's chemical potential in the supersaturated and saturated solution, increasing the average size of the product and avoiding further nucleation. We wrote also a simulation program in QBasic, the program at the time. It was rather good. The experimental data were in good agreement with the predictions, and it was possible to reproduce faithfully the influence of the cooling profile on the crystal granulometric properties and the effects of all the operating variables except with heavy seed crystals. We can see the small difference between the lines. The continuous lines are the simulations, while the points are the experimental data. The red line is almost perfect. Conclusions. In the years 1997-1998, at the AGMA lab of La Sapienza University, we analyzed the batch cooling crystallization of the citric acid monohydrate CAM from aqueous solutions. The choice of a light seed optimized the process by avoiding subsequent nucleation and increasing the average size of crystalline product. Looking for a homogeneous distribution of large crystals, we found that temperatures slightly above the spontaneous nucleation, namely T equals to 22 Celsius degree, was the most effective to reduce the negative incidence of a low initial supersaturation and the negligible surplus seed. The experimental work was supplemented by a QBasic program to predict the CSD, the crystal site distribution. The list of acknowledgements is huge, it's very long. And of course, I'm grateful to the organizers of the 9th conference in Odessa AGMA. Thank you very much.
Okay, thank you for the interesting talk.